So panel data one is the different from the cross-sectional and time series data. So in a cross-sectional data, we have only cross-sectional component, and in a time series, only time series component. But in a panel data case, we have both time series and cross-sectional component. So in writing, okay, so when we write our regression model, we write cross-sectional regression model like this, okay, as usual, and time series regression like this. So in a cross-sectional regression model, I represent ith cross-sectional unit, and in a time series, T represent time period. In a panel, since panel data includes both time series and cross-sectional component, so when we write regression equation, we include both I and T and write our regression equation yit equal to beta 1 plus beta 2 x2 it plus uit. That means all the uh, uh, variable here having both cross-sectional and time series components. So this one is the standard way of writing different kind of regression model. So, so the question arises, why do we use panel data? So the answer of it lies in its advantages. And the first advantage of doing panel data, it gives us larger number of observations. And we know a larger number of observation is good for DNA model. A larger number of observation I mean here, since you are working with the 100 cross-sectional unit with 10 year of data set, so in that case, you will have 100 into 10 equal to 1000 observation. But if you go with the time series or cross-sectional regression model only, so in a time series case, we will be having only 10 observation for 10 years, and in a cross-sectional case, we will be having only 100 observations for a particular year. But when we combine both time series and cross-sectional things, we get a larger number of observations. So that one is the one biggest advantage of doing panel data regression model. Second advantage is it increases precision in the estimation. And that is because we get more informative data set having a higher variation, data set suffer with the lesser degree of correlation or no correlation. And of course, you will have a higher degree of freedom. So these are the, we can say the regions which increase the accuracy of our estimation. So first we will get more informative data. Of course, more informative data because you are having a larger number of observations. Since you are having a larger number of observations, so data set having a more variability. And more variability causes less collinearity. And again, more data, larger number of observations causes larger degree of freedom. Third advantage of doing panel data regression model is it control unobserved cross-sectional heterogeneity that may be related with the any of the explanatory variable included into the model. And if that is the case, using OLS estimator, we get biased and inconsistent estimates. But panel data take a control of that unobserved heterogeneity and give us consistent estimates. Of course, unbiased and consistent estimates. And this one is the major advantage we can say that doing a of panel data regression. The fourth one we can say it captures the dynamic of changes. Like if you want to study the changes in employment, unemployment, changes in job turnover, uh, labor mobility are better captured through the panel data. So, you may heard about earlier an SSO used to do a cross-sectional survey of employment and unemployment situation till last year, and it is since 2017 18 NSSO started doing a panel data survey, and that comes in a form of periodic labor survey. And that one is because panel data is able to capture the dynamics of employment and unemployment situation. Uh, Fifth advantage one is panel data is better to detect and measure that we can't simply do with the either cross-sectional or time series data. Like effect of minimum wages law on employment. So if you want to capture this particular effect, then of course we can't do either with the cross-sectional data or with the time series data. For capturing the effect of minimum wages law on employment, you must uh, having a panel data. So these are, we can say, some of the advantage of panel data. So let's move on to the type of panel data. So when we start working with the type of panel data, we need to know about what is balanced panel, what is unbalanced panel, what is short panel, and what is long, long panel. So as written here, the short panel, we can say panel data, one is the short panel data when number of cross-sectional unit is greater than number of time period. So I mean to here, if n is having 1000 and t is 10, so time period is for 10 years only, and cross-sectional unit is 1000. So in that case, we can say we are having a short panel. Long panel, again, when time period is greater than number of cross-sectional unit. So in this case, suppose that you are having a 50 year of data, but cross-sectional observation is only 10 or 20. So in that case, we can say the panel data, one is long panel data. We'll talk about the more short panel and long panel, why you have categorized panel data into these two parts and how it uh, uh, going to affect our estimation when we actually do fixed effect and random effect regression model. Or we can say when we actually apply fixed effect and random effect methods for estimating the panel data regression model. But we'll come on to that later. So we'll discuss more about the panel data and short panel data, or we'll keep discussing about the uh, along with this lecture. So let's understand what is balanced panel and unbalanced panel. So balanced panel is when you are having data for all cross-sectional unit for all year. That means whenever there is no missing data in a data set, we can say the data set is balanced panel data set. So for this, let's take an example. You are having a 1000 cross-sectional unit and time period is for 10 years. So with this, we assume that number of observation is 1000 into 10, that one is a 10,000. And for this 10,000 observations, we will be having one specific value for each cross-sectional unit for each time period for all variables. So in that case, we can say that our data set is balance panel data set. That means no missing observation. Whenever you are having a missing observation, that means we are having a unbalanced panel. So, so this one is about the unbalanced panel. So with the missing observations, that means data set is panel data set is unbalanced panel. In this course, we will deal only with the uh, balance panel and specifically with the short balance panel. Short balance panel, I do not mean to number of observation is we are expecting that you are going to deal with a model which or we are going to deal with a data set which contains a lesser number of observations. No, I mean short balance panel, I mean to say you are going to deal with the short panel along with the balance panel. That means when we have substantially larger number of observations as compared to the number of years. So, so the regression model with which we can deal in this course, one is the pooled regression model, fixed effect, least square dummy variable regression model, then fixed effect model and random effect model. So fixed effect and random effect are basically the two methods. Okay. So whenever you apply the fixed effect method for estimating the parameters of panel regression model, we can say the model is fixed effect model. And whenever we apply the random effect method for estimating panel data regression model, we can say our model is random effect model, nothing else. So let's do the full regression model first because it is easy to do. It doesn't require much, you can say, understanding of panel data regression model. It is as like the OLS regression model. So this one is our regression model. So you are having a dependent variable denoted that with y. I and t are the time cross-sectional and time series component respectively. Betas are parameters. Variable are x1, x2, x3 up to xk, and u1 is the error term. In a matrix form, you can write this one is yit equal to xt beta. So x1 is the vector of matrix here. Okay. In book, you will find this one is bold term. So, so, so the x, wherever I have written x, that means that x is a vector of explanatory variable, and x is written there in a matrix form. Beta 1 is the parameter of interest, and u1 is the error term. I we have not included here I, and that one is the usual notation used by the Woodridge in his book Cross Sectional and Panel Data Econometrics. So we may include, may not include. Okay, that up to you. But Woodridge, in a Woodridge sense, Woodridge say whenever Woodridge use I subscript, that means that variable belong to a particular cross-sectional unit. So we are going with the unit. So I omitted I from here. So that one is the only xt beta plus ut. But you can read this one is XIT. That means it doesn't mean that this one X belongs for a particular year only. Not only belong to a particular year value, but it also belongs to a particular cross-sectional value for that particular year. So xt is here 1 into k vectors, and for and t is equal to 1 to t. Beta is a k1 into 1 vector. So, so this one is the usual notation of writing a panel data regression model in a matrix form. So before going on to the estimation of OLS, let's discuss first when we consider our data set as a panel data, or when we consider the same data as a pool data, because both of the panel data and pool data are having the cross-sectional and time series component. So let's understand this. When we consider a particular the same data as a pool data and the same data as a panel data. So in a pool data case, we do not bother about the order and sequence of the data, and this one is the most important thing, the differentiating between pooled and panel data set. So when we do pooled regression model, we actually do not bother about the order and sequence of our data. But in a case of panel, we indeed bother about that. So we can say in a pooled case, we simply collect cross-sectional unit value and time series value, combine those value either using Excel or any other particular software, and made our data set. So when data is simply pooled for each cross-sectional unit over period of time, that become a pooled data set. In a panel data set, as I told to you, indeed bother about the sequence of the data. So this one is the example of panel data. So here you are having an observation 1, 2, 3, 4, and so on. This one is the cross-sectional unit. So here I have taken only 5 cross-sectional unit. So, and each one having a unique ID, and that is here 1, 2, 3, 4, 5. So sorry, not one. Sorry, here I am having a 5-year data, and 3 cross-sectional units. So the exemplary data set is here, in which I have included only 3 cross-sectional units. But we know in a panel data case, we generally have more cross-sectional unit time uh, than time component. So here you are having a only 5-year data set. So what we do in a panel data, first we assign unique code to our each cross-sectional unit. Unique numeric code I am talking about. So as I here assigned 1, 2, 3, but actually when we work with the panel data, we require to assign unique ID in a such a way so that that unique ID remains same irrespective of, you can say, different data set. That for example, let's maybe open the whiteboard. So let's suppose that you are working with the FAO data set. Any one of you have worked with the FAO data set? Or I'm talking about the FAO data set. So even if you haven't worked with that, or we can say the World Bank data set, or ILO data set, because these are the data depository which provide us uh, mm, uh, panel data, or we make panel data combining uh, cross-sectional and time series data file, or even with the RBI. Okay, so RBI also provide a time series data set for at least for at a state level. So let's suppose that you are going to study the 17 states performance. We can say performance 17 major states I am talking about. Okay, 17 major states performance in terms of their GDP, over 1990 to 2020. Okay, so in this we are having a 21-year data set, and 17 are the cross sectional unit. So of course you are not going to get data set, probably will not get going to data set of GDP of all the states over period of time in a one data set, in a one data file. You may get a 2 or 3 data file, and only when we combine these 2 and 3 data file, we will get to get the final data file which contains information of these states GDP over period of time. So this one is the only with the one variable. Suppose that with the GDP, we also want to look the total social sector expenditure, total social sector expenditure, social sector expenditure, and and you want to establish a relationship between the GDP and total social sector expenditure. So in that case, we need both of these two files. And after combining both of these two files, we'll able to have a request all information in a single file. So working with that RBI data set seems easy, because uh, even in this case, though it is easy as compared to working with the FAO data set and World Bank data set. So since here you are having only 17 cross-sectional unit, so we assign unique code to each cross-sectional unit, and we will keep this unique code remain constant for the other data set also. So if one is belong to Bihar, then in a one data set, one code belong to Bihar, and the same code you want to keep for Bihar into the other data set. So in that way, we keep unique or you can say the unique identity code remains same for each cross-sectional unit in all data sets. But what if you are working with the 1,000 cross-sectional unit, or we can say 198 cross-sectional unit? 100, 198 I am quoting here specifically because when we work with the FAO World Bank data set and we try to gather different information for at the world level, or you can say the all country of the world, then for some year you may get an observation for 200 country, in some year 100, 215 countries, in some year 290 countries, particularly when we work uh, uh, after 1990, when we gather a data for after 1990. So In after 1990, okay, it also depend upon for what value, sorry, for what variable you are gathering the information. So, so with one or two variable like GDP and total expenditure case, you may end up with a 198 cross-sectional observation for which you are value for which you are having a value for all the years after 1990. So I am trying to say here, when we gather information as such like in a such a way where you have to deal with a different data file, and each data file contains a different number of cross-sectional units. So giving a unique identity to each cross-sectional unit is very difficult. Though in this day, with the invention of software, it's become easy, but you have to know about that. So of course we'll deal with this when we actually work with the panel data set. Okay, uh, or we can say when we actually do the practical exercise using the panel data set. Now I am discussing the theoretical aspect of the panel data set. So in a panel data set, assigning a code is very important, and that code remains same for all cross-sectional unit uh, in all data set. You may think to use uh, a thing to take a help of Excel, but Excel doesn't work uh, uh, any, uh, any, that effectively. Even chances of doing mistake in Excel is greater. I think if you are familiar with the World Bank data set, say World Bank data sets comes with the code. World Bank data sets comes with the country code. Country code. Okay. Like for India, that one is IND. IND represent India. So something like that. So for each country, World Bank having a one country code. So with the working with the World Bank data set, we'll take a help of that country code, but unfortunately that country code is a non-numeric value. So it required to transform this country code into a numeric value. Because for panel data set, we required a unique country code in a numeric value instead of non-numeric value. So I'm talking about I'm just letting you know or acknowledging you that there is a particular command in Stata. That one is basically a uh, not a Stata own command. That one is the user written Stata command that help you converting the non-numeric code into a numeric form. The same in the case of ILO. ILO used a different code as compared to the World Bank. And uh, same with the FAO. FAO used a different country code as compared to the World Bank. And when I were working with my PhD, I were working with the World Bank dataset and FAO dataset. And I found really hard at that time how we combine two different data files which are having a different identity or a different unique identity. So though at that time initially I was discussing with the 78 countries, so uh, I took a help of Excel, but again it's not only with the 78 observation. Okay, at that time we were having a many variable, okay, and then 78 observation. So matching one observation of one file with the other observations with the other data file, one is very difficult. But if you spend time and if you are able to match 1:1, so let's suppose that India contains code 10 here and here 11, so you may convert that one in the 10 there. But that takes a lot of time. Again, I am telling there is a particular user written command through which we can convert codes into numeric, and then after we sort the numeric and assign you can say change country data code. So assigning a Unicode one is very, very important. Then after you are having a year, then after having a value of y and x. So in a panel data case, look here, first you are having a cross-sectional unit. So the first type observation one is the cross-sectional unit observation for cross-sectional unit 1, and then after you are having a years in a order. First we are having a 1990, then after 1991, 1993, 1992, 1993, and 1994, and then values. So these has our values basically. So here you are having a data set in a particular sequence. After then you are having a second cross-sectional unit, then data of second cross-sectional unit for different years in a order, and so on. So this one is called a panel data, and data format is called here a longitudinal data set. So when you work with the panel data, you must ensure that our data set is in a longitudinal format. For a full data set, we do not bother about it. As I told you earlier, in a case of full data set, we just pull cross-sectional and time series component without bothering about the sequence of the data. So here you may have first few observations for a particular cross-sectional unit over a period of time, and then second, then third, and so on. So here, as I shown you example, the first three observations belong to cross-sectional unit 1. Then you are having a 3-year data, again in a not in a order. First one belonging to 1990, the second one belonging to 1991, and the third one belonging to 1994. Then we have two cross-sectional. Then we are having an information for second cross-sectional unit for 2 year 1990 and 1991. Then after again you are having a cross-sectional unit, first cross-sectional unit that we have coded with 1 with 1990 year, sorry 1992 year data. So in a pooled case, again I am saying we do not bother about the sequence of our data set. So So that's about the arrangement of the data in case of pooled and panel. So again, I am reiterating, when we work with the panel data regression, we must ensure our data set is in order. And in case of pool, we do not require to do so. One more assumption that we call the implicit assumptions, that in a cross-sectional, in a pooled case, we implicitly assume that each cross-sectional observation is independent from each other. So there is no correlation across cross-sectional unit over a period of time. So that means each observation is independent observation. So these are the assumptions, but before going on to the assumptions, I would like to take your doubt. If anyone having any doubt, please ask from me.
So I have a little doubt.
Yes.
Sir, regarding the pooled and panel data model, so we can always arrange the pool data like systematically. And so why do we have another model? Because will the sequencing change the results from the regression?
Yeah, of course. And sequence change, result of the regression will change in case of panel, but not in a case of fold. Answer will be like when we will talk about the assumptions behind the fold regression model.
Okay, sir.
So we are going to discuss that. Any other doubt? Okay. So let's discuss the assumptions of fold regression model. So first and foremost assumption, we assume no correlation between explanatory variable and error term. So that one is expected value of x prime t ut equal to 0 for all t. Second one is the rank assumption, full rank assumption, and this one is needed for identifying each parameter. Third assumption one is basically no heteroscedasticity assumption. So when we say expected value of u square t x prime t x t equal to sigma square expected value of x prime t, and sigma square is nothing else expected value of square of error term for all t. So this one is the homoscedasticity assumption or no heteroscedasticity assumption. The B part of third assumption one is basically related with the no autocorrelation assumption. So here we are assuming error terms are not correlated with one another. So ut us x prime t x t equal to 0 when t not equal to s. And these all are the usual OLS assumptions. So in a case of OLS, I mean classical linear regression model case, when you use OLS, so again in that case we assume all these things: no heteroscedasticity, no autocorrelation, no perfect multicollinearity. That one is here taken care by the full rank assumption, and no exogeneity. Sorry, no endogeneity. So so that one is the taken care of by the expected value of x prime t ut equal to 0. If you diagnose our assumption, then you can see that the first two assumptions are sufficient for pooled OLS for consistently estimate beta. And that we know. Even when regression models suffer with the problem of heteroscedasticity and autocorrelation, we get unbiased and consistent estimates of parameters. First assumption ensures that there is no correlation between XT and UT for our cross-sectional unit. But it says nothing about the relationship between XT and UT when T not equal to S. So when T and S are different, then in that case, that assumption is silent. So that assumption only belongs when and we are talking about the both variable x and ut for a same air. So when t equal to that means when t equal to s instead of when t not equal to s. And assumptions too, which one is the full rank assumptions? As I told you, it rule out any perfect linear relationship between explanatory variable. Later, heteroscedasticity and autocorrelation assumptions, as I so are useful for estimating the efficient estimates of parameters. So with all these assumptions, we will get a asymptotic variance of beta hat. The formula is written here. I'm not repeating that. And since we require to estimate the sigma square also, so our estimator of sigma square is sigma hat square, and that we are able to get when we run regression model y on xt. because for estimating that will be needed a estimated residuals square. And when all assumptions satisfy, that means T and F statistics are uh, valid. So, so the pool is same as like uh, OLS in a cross-sectional case. And why it is so? Because as I told you, we implicitly assume in this case all observations are independent from each other. That means assuming this, you are ignoring time series component. We are not bothering about the time series component. So excluding the time series component, that means that is the same as we deal with the cross-sectional data set. And that's why in a pooled case we require to assume all assumptions or required to test all assumptions whatever uh, all cross-sectional regression model assumptions or all assumptions uh, that you have studied in case of OLS. So or anyway in a pooled case we are using OLS, so we need to ensure that our regression model satisfy all those assumptions. So that's why those assumptions are mentioned here too. Now let's move on to the dynamic pooled regression model. So in a case of dynamic pooled assumption, the assumption relating to the heteroscedasticity and autocorrelation must to be hold. And we know in a dynamic regression model, either you are having a lag value of dependent or independent or both in a regression model as like this. In a basic econometrics textbook, okay, particularly in a Gujarati, probably you have noted down when you work with the uh, regression model in which lag value of dependent variable is an explanatory variable, and in that case when we found our autocorrelation, then our OLS estimator become a inconsistent estimator. But Ulrich argued here that this is not the case always, that is statement is true in a context of a specific model. And Ulrich argued here if expected value of yt given t equal to xt beta, then irrespective of whether ut is serially correlated or not, in general we will get a consistent estimates of the parameters. More about this is given in Ulrich cross-sectional and panel data econometry books on page number 196. We may go through that. Here Ulrich mentions a reference reading for it. I haven't gone through that reference reading, but if you want, but in a case you feel to know more about this particular aspect, then you must go through that. Some note on time series persistence, but in this course you are going with the deal with the dynamic panel data also. So more we will talk about the dynamic at that time. But but even in a basic panel data case, you are both having a time series and cross-sectional component, and we know for a time series there is an entire you can say and the time series is entirely a different subject, okay, or separate subject in econometrics. So whenever you deal with the panel data, we also need to note down something related with the time series data set, and that you are going to talked about now. So, so here is, if n is sufficiently greater than t, then you do not need to worry much about the time series persistence. That sometimes, I mean, to sometimes you may think to, okay, we are dealing with the panel data which are having both time series and cross sectional component. So why we are not bothering about the time series econometrics? Okay. We might require to use a time series econometric concept while dealing with the panel data regression model. So the answer of that, whenever we work with the panel data where n is sufficiently large, then t part, in that case you do not need to bother much about the uh, time series component, or the persistent of time series. This one is the particular persistent of time series. Sometimes in a data set you are having a time effect that you are ignoring here. Okay, probably in the next few slides we will talk about this one, time series persistence also. So assuming that assumption 1, 2, 3 holds for the pooled OLS, persisted consistent estimates of parameter. So, and that happen only when n is sufficiently large as compared to t. But what if n is small relative to t? Let's suppose that in our earlier case I was discussing, when you are having only 10 time series component, 10 cross section component and 50 time series component. So in that case, of course, we bother about the time series econometrics aspect in the data set. And that may relate with the stationarity condition. You may heard about this one, stationarity, non-stationarity. If you do not deal with that, then the time series, you can say the persistence part create a considerable problem. If even in a case of, you can say the asymptotic case. So basically, when we talk about the asymptotic properties of any estimator, so with the asymptotic properties of the estimator, basically you are approximately estimate the proper, or you can say it approximately uh, guess or estimate the properties of properties of finite estimator. So finite finite properties estimator is the approximation of asymptotic properties estimation that we have done in the last semester. So that one is, even when we deal with the things asymptotically. So, and if you're working with the large panel data set where n is sufficiently small as compared to t, so when t tends to infinity, okay, you require to assume stationarity condition. Otherwise, it causes a considerable problem. So these are the two notes of the time series persistence. So you must remember, whenever n is sufficiently large compared to t, do not bother about the time series uh, econometrics part, or using the time series econometrics in a panel data case. But in a case when n is small compared to t, in that case we indeed bother about considering time series, using a time series econometrics in a panel data case. These are the, you can say, the diagnosis test and remedial measure. So all usual OLS diagnosis test is done in case of pooled regression model 2. Like if you get a presence of heterozygosity, autocorrelation, then suitable remedial measure need to be adopted for getting efficient estimates of parameter. Drawbacks of pooled regression model are, in a case of presence of unobserved heterogeneity, we get bias and inconsistent estimate, particularly when, or sorry, uh, in a case of presence of unobserved cross-sectional heterogeneity, even though that is not related with any of the regression, the estimator become inefficient. But in a case when unobserved cross-sectional heterogeneity one is related with the any of the explanatory variable, that means that violate the assumption of endogeneity, and in that case we will get biased and inconsistent estimates of parameter. In earlier also I told you do panel data set because of this unobserved heterogeneity thing. So, so in the presence of unobserved heterogeneity, two conditions arises: either that unobserved heterogeneity one is related with the explanatory variable, or that one is not related with the explanatory variable. So even that unobserved heterogeneity is not related with the any of the explanatory variable, that means if you use pooled OLS, you will get inefficient estimate. But in a case if that one is related with any of the explanatory variable, we get bias and inefficient estimate. So I'm writing down an equation for getting more uh, understanding on that. Let's suppose that you are having a regression equation like this. So beta 2 x2 it, I'm writing a linear regression equation. So beta 3 x3 it plus c ci plus uit. So I'm adding here one extra component, that one is the ci, and let's suppose that this one is the unobserved heterogeneity for time being. Okay, before I am going to explain what this ci, why I have written ci here. Okay, so let's suppose that this component one is the unobserved heterogeneity, which we consider as a random variable. So unobserved heterogeneity, and this one is the relating with the cross sectional unit. Cross sectional unit. So if this is the case, then with the in a case of presence of this unobserved heterogeneity, I am saying even though it is not related with the any of the explanatory variable, if you use pooled OLS, we get inefficient estimates. Why we get inefficient estimates? We will discuss about it when we actually do a random effect regression model. Because unless or until you do not understand about this random effect regression model, I think I think it's hard to understand why there is an inefficient estimate. Okay, but better if you move on to this topic after doing the random effect estimation, because when we are talking about the assumptions, let's suppose that the assumptions we are saying that ui and us equal to 0. That means the time uh, an error term of ut, not I, ut and s equal to 0. So t belong to one time period, s belong to one time period. So for each cross-sectional unit, we are assuming that there is no autocorrelation between error term. But in that, we miss to assume about the relationship between error term of ith cross-sectional unit at t time period for j cross-sectional unit at t time period. So what about this assumption? And because of this particular thing, okay, not only this, there are something more, a few more things about which we need to talk about before talking about why we get inefficient efficient estimates in case of OLS in the presence of unobserved heterogeneity. For time being, we just know that in a case of presence of unobserved heterogeneity, we get efficient estimates. But in a case, as I said, when Ci1 is correlated with any of the explanatory variable, then in that case, regression model violate exogeneity condition and we will get biased and inconsistent estimates. And that true in case of random effect also. And because of that reason, we use fixed effect. So what here you are having? Here you are having a pooled, you are talking about the pooled. So I'm saying the pool is inefficient as compared to random effect. In a uh, in a presence of unobserved heterogeneity, and random effect one is, you can say, give a bias and inconsistent estimate if there is a correlation between unobserved heterogeneity and explanatory variable. So the best model when unobserved heterogeneity is correlated with explanatory variable one is the fixed effect model rather than pooled and random effect model. So any doubt? Because you are going to move on to the fixed effect least square dummy variable model. That one is the second model uh, of pool data set. Sorry, of panel data set. Any doubt? So can you hear me? At least say yes, no. So in the case if you do not have any doubt, so let's move on to the second model. That one is the fixed effect least square dummy variable model. Okay, so I'm using this name because Gujarati has used this name. Sometimes in some books we have only least square dummy variable model. But least square dummy variable model, like even when we do not, even when we work with the cross-sectional data set and when we apply dummy variable regression model, we may name that as a least square dummy variable model. So just to differentiate with that, I have used here fixed effect least square dummy variable model. Fixed effect because the result of this particular model and fixed effect model are approximately same. Why it is so, we'll talk about this later, of course, but let's understand what this fixed effect dummy variable model is and how do we estimate this particular model. So again, this one is the as usual equation of a regression equation model in matrix form. So xt is 1 into k vectors, and in this particular model, xt contains cross-sectional dummy. So in a pooled case, we haven't included cross-sectional dummy variable as a explanatory variable, but in this particular model, we are going to deal with that. That means in a pooled case, by writing that in a algebraical form, so yit equal to beta 1 so beta 1 plus beta 2 x2 it plus beta 3, so beta 3 xit 3 plus uit. So uh, so you are here, you are having a two explanatory variable x2 and x3. So we may assume both of these are continuous variable or one dummy variable or one continuous variable. But of course, these variables are not cross-sectional dummy variable. Even if you add the cross unobserved heterogeneity component here, so this one become a part of BIT1 is the combined, you can say, the error term, which include both CI and UIT. So this one is in case of pooled, you can say the pooled. Okay. And again, I am saying pooled might be without unobserved heterogeneity and with unobserved heterogeneity. And in case of uh, fixed effect least square dummy variable, we write B1, the same regression equation, B1, B2, XIT, B3, X3IT, plus here the cross-sectional dummy. So if you are having a n equal to 1000, which one is the cross? Sorry, yeah, any cross-sectional component. Total number of observation is NT here. So this one is the number of observation. Okay, so any cross-sectional component in our framework, T is time period. So if time equal to 10, so NT1 is, which one is the total number of observation? Going to be the 10,000. So this one is the 10,000. So in a fixed effect least square dummy variable case, you are having a 999 dummy here. So you may start with here delta 1, D1 plus delta 2, D2 plus so on, and delta 999 D 999. Then after we have UIT term. So this, the later one is a fixed effect least square dummy variable. So differentiate between the pooled and fixed square dummy variable. So here you are having adding a cross sectional dummy variable. So with the 1000 cross sectional unit, we list one less dummy, 999 dummy. So base dummy one is 1000 cross sectional unit. So that one is the case. Again, in this case, you use OLS to estimate the value of parameter. And again, we ensure that all assumptions of classical linear regression model satisfy, so that we get consistent estimates of the parameters. And this regression model works well even when regression model has cross-sectional heterogeneity, cross-sectional unobserved heterogeneity. So cross-sectional, you may add here unobserved heterogeneity, not only heterogeneity. So unobserved heterogeneity problem, cross-sectional unobserved heterogeneity problem. So, and it's not only the presence of unobserved heterogeneity, even though that heterogeneity related with the any of the explanatory variable included into the model, fixed effect least square dummy variable model takes care of that problem and give us consistent estimates of parameter. Try to understand, I am talking about in a earlier case, this one is our model, fixed effect least square dummy variable. So I am saying that this model works well. So this model works well even when there is a presence of cross-sectional unobserved heterogeneity, and second, when that unobserved heterogeneity is related with any of the explanatory variables included into the model. And that is because using cross-sectional dummy automatically take care that unobserved heterogeneity. And since when we read more about that cross-sectional heterogeneity, we can see that we will be talking about the time constant unobserved heterogeneity. That means that unobserved heterogeneity one is time invariant, that is not changing over a period of time, and that one is belonging to the cross-sectional unit. So it might be said say that the cross-sectional unit is individual person unit. So the cross-sectional unit in our case is individual person or individual firm or individual country. So we know that each individual having some special characteristics, each country having a special characteristics, each firm having a special characteristics. Some are more efficient, some are less efficient, probably because of managerial capacity of that firm or worker of that firm are more efficient. In an individual case, maybe one person is more able because of he or she is more intelligent, or he or she having a more ability because of intelligence. A country is more special because of you can say uh, its hereditary things or cultural things or custom because of custom things. Okay. So that one is taken care by using individual cross-sectional dummies. Because we know we use dummy for a qualitative variable, and when we are talking about the unobserved heterogeneity, basically we are talking about those quality, even though those are unobserved. Because the custom, you can't measure custom, you can't measure culture, you can't measure anyone's ability. So if that is the case, and for accounting that, if you are using cross-sectional dummy, then cross usage of cross-sectional dummy automatically take care of that unobserved heterogeneity, and whatever estimates you will get, that one is unbiased and consistent estimate. Then question arises, what wrong with this model? So answer lies in the drawbacks of this model, and the drawbacks are, in a case of short panel, as we seen earlier, when you are having an 1000 cross-sectional unit, you require to add too many cross-sectional dummies. And for adding a too many cross-sectional unit, particularly when T is relatively, you can say small, because you are working with the small panel data, there are chances of losing a substantial degree of freedom. Like in earlier case, suppose that T equal to 2 only. Like suppose that in our earlier case, in this case, let's open a new thing. Suppose that in this case, with the T equal to 2 or 3, okay, and when N equal to 1000, if you add 999 dummies, and let's suppose that you are dealing with the 5 explanatory variable, then in that case, we lose 1004 plus 1. That one is the constant of degree of freedom. So the actual degree of freedom with the 2000 minus 1005, then that one is 95. So degree, we lose substantial degree of freedom when we work with the larger cross sectional unit with a smaller time period. And that one is the, you can say, the one draw, the one major drawbacks of panel data. But with the larger time period, of course, even after losing the uh, degree of freedom, will end up with a substantial degree of freedom. So that not that much that serious problem. Okay. But with the smaller time period, there is a chances of losing substantial degree of freedom. Second drawback of the model, it increases the chances of having multicollinearity problem. The multicollinearity goes up when we increase so many dummies into the model. Third one is it compromises the concept of parsimonious regression model. So this one is the concept that we probably studied at your undergraduate level. We keep our model as short as possible, of course, by including all explanatory variable. So in that case, this model compromises with that concept. And the last one is we can't estimate the impact of qualitative explanatory variable. So qualitative explanatory variable, let's suppose that if in our area regression model, we are also having a gender component. So for that, we will require to include a gender dummy variable. But again, that gender one is relating with the cross-sectional unit. So in a fixed effect dummy variable case, we can't get the impact of gender on Y or any of the qualitative explanatory variable, because again those are remain constant over a period of time. So, so these are the drawbacks. More about the model, we you can say this one is the single side of the effect list is quite a variable. When we do fixed effect, then we compare the result of fixed effect least square dummy variable with the fixed effect uh, regression model result, and there we will talk about few more things on. One thing has been left in a case of contemporaneous correlation case, when error term of I at time t is correlated with error term of j at time t, we get inefficient estimates with fixed effect least square dummy variable. Okay. So contemporaneous correlation again we'll talk when we work with the fixed effect model. Okay. So this much for today. The reference reading are Gujarati for essential reading. You may have a look of Woodridge book also for essential reading. Woodridge, I am talking basic econometrics Woodridge book. The advanced one is your textbook. So whatever I have covered into this slide, a few part of it, particularly the essential slides, sorry, initial slides of these presentations are from Gujarati book, where you are talking about the advantage of having a panel data model. Rest start from the Woodridge book, and that one in the chapter, from chapter 7, particularly section 7.8, page number are mentioned here. So any doubt? If you are having any doubt, then let's discuss that. So, okay, fine. So this much in this lecture. In the next lecture, we start with the random effect model. Of course, uh, Before jumping onto the random effect model, we'll bring the concept of unobserved heterogeneity. We'll discuss unobserved heterogeneity in details, considering that one is the explicit component uh, of a regression model. So earlier I have written here there CI. So it include CI into a regression model. Talked about the nature of that CI. What if that one is a correlated with the explanative variable? What if not? What kind of assumptions are needed uh, uh, for that? Because that one is the unobserved component, so you do not have uh, a data of that. So in absence of that data, that become a part of error term. So that is a composite error term BIT. So we'll talk about the uh, nature of that BIT, properties of that VIT, and assumptions needed relating to VIT for estimating random effect model. And after having that, we move on to the fixed effect model, and we'll discuss many more things there. So, so that one, I think, for next lecture. So if you are having still any doubt, then discuss that with me. Otherwise, I will end this call and will share with you this presentation and also recorded lectures. Okay, then fine. So thank you.